This video is meant for the entire concept of axial loading in a single video. So we call this by the name Capsule of Axial loading. Capsule of Axial loading. From the previous lectures, we have told you that axial loading is the loading that we provide on a particular member in the normal direction, that is normal to the cross-sectional area. Let this be some W that we apply on the normal area. Let's suppose this is the normal area of this particular member and we are applying it like this. Okay, so the load is normal to area of cross section. So that's about the axial loading, and we are having two possibilities of sign convention. That is, if we are applying a load that is acting out of the cross section, that is tensile, and we treat it as positive, and we generally treat it as positive, and we are having, or when some force is applied towards the cross section of the particular member, then it is called the compressive stress or compressive loading, and generally it is treated as negative loading. Okay, that's about the axial loading thing. And then we have dealt with stresses and strains. Generally, stress is given by the equation P by A, and strain is given by the equation epsilon is equal to delta L by L. And we know that the unit of this particular term stress is Newton per meter square, which is SI system of unit. And this unit is very small, and this represents only very small quantities. So we generally use Newton per millimeter square. It is called as megapascal, and this is Pascal. This is denoted as PA, and this is denoted as capital M PA. And generally, this epsilon, that is nothing but the strain, is not having any unit, because delta L is generally in mm and L is also in mm. So cancelling these terms, then we will be getting no unit for a particular strain. And this stress is nothing but the internal resisting force, that is internal resisting force generated within the material due to the external applied load per unit area. That is the important thing, per unit area. And strain is the ratio of change in dimension to original dimension. Since we have limited our discussions to only one dimensional change, that is along the length, epsilon is treated as delta L by L. Okay, that's about stresses and strains. And then we have dealt with some terms called the elongation, Hooke's law, something like that. And it was experimentally determined that for some structural materials, stress is directly proportional to strain up to a certain limit. So we can draw it as like this, and this particular limit of stress is called the proportional limit. So we can relate this relation as sigma proportional to epsilon up to proportional limit. Okay, so we can eliminate this proportionality constant by providing some constant into epsilon, where E is nothing but the Young's modulus, and which gives a measure of resistance to elongation or deformation. That is, we can see that epsilon is proportional to 1 by E, which means as E increases, epsilon decreases. So increasing the value of E, which will further causes a reduction in deformation or the change in length. That is nothing but the strain. Okay, so that's we have dealt with elongation and Hooke's law, and then we have provided that we are having some universal equation of axial loading. Universal axial loading equation, that is from the equation sigma is equal to P by A, and also from this particular equation of sigma is equal to E epsilon, sigma is equal to E into epsilon, which is E into delta L by L. We can write delta L is equal to PL by EA. I will write it over here. Delta L is equal to PL by EA, which is nothing but sigma L by E, and this can be used for the determination of elongation of the length only when P comma A comma E is constant along length of member under consideration, and this equation is the universal equation of axial loading. Okay, and then we have dealt with something called the longitudinal stiffness, and which is nothing but if we compare the member that is subjected to some axial load like this with respect to that of a spring that is subjected to some axial force P like this, and we know that the elongation delta L that is caused due to the load P is equal to PL by EA, where L is the length of this member and E is the Young's modulus of this particular beam for the member that we considered, and A is the cross section of this particular member. Okay, so this is the equation of elongation for this particular member under consideration, and we know that for the spring which is subjected to some axial force P, delta L will be equal to P by K. So comparing these two equations, where K is the stiffness of this particular spring and delta is the change in length and P is the applied force, and comparing these two equations we can write the stiffness, that is longitudinal stiffness K is equal to EA by L, and this is having some implications in problem solving. Okay, so then we have dealt with the last concept of this particular axial loading is the thermal stresses, and these thermal stresses originate on some members under consideration only when it is subjected to some change in temperature. Say if we are provided with some coil over this particular shaft and then we have heated it, then what happens is the temperature changes, and if the temperature change is increasing, then expansion occurs, and if temperature decrement is occurring, contraction occurs. Please note that these temperature change and temperature increment or in temperature decrement will not cause any stresses in the material, and the stress will be generated in the material or in the member only when this expansion or contraction is prevented. Sigma occurs when expansion or contraction which is caused due to the increase in or decrease in the temperature is prevented. Okay, I also note that if expansion is prevented, which will cause compressive stress, and if contraction is prevented, then which causes in tensile stress. So please note these two important points in your mind. So upon application of this temperature, then we will be getting some kind of this elongation of this particular number, which is represented as delta LTS, and it is given by the equation alpha delta t into the original length. And we know that strain is nothing but delta L by L, which is given by the equation delta alpha delta t. We know that sigma is nothing but E into epsilon of Newton's law. So we can write sigma th, that is thermal stress, is equal to E into alpha delta t. So that's it. These are the entire concept that we dealt in this particular